recall an exact sequence, it's exactly every one of these modules. That means the image of this homomorphism is kernel the next, the image of this is kernel the next, and so forth. So this means when you have short exact sequence, the first map is 1-to-1, the last map is onto, and in the middle, the kernel, or I'm sorry, the image of F is exactly equal to the kernel of G. This one actually is called, so we did some examples last time. I'm going to define this later, but here's kind of a special case. You have this. You can always make a short exact sequence this way, where this is inclusion on the A. So in other words, A goes to A0, and we'll call this projection on C, where this takes the input AC and just reads the C coordinate. Notice that the image of this map is just everything in the form A comma 0, which is precisely the kernel of the next map, because what it means to be the kernel of this map is you have to have 0 in the second coordinate. So this one is actually called a split. So what it means to be split exact is that you can basically run the sequence backwards. Notice that in each case, there is a function, we'll call this inclusion on C, and there is a function that goes back here, projection onto A. So you can run this in reverse, right? So you can go C to 0 comma C, and then AC to A, right? Notice that this composition here, what happens when you do this composition? You start with C, and you go to 0 comma C, and then you project back against C. So when you do this projection here, or this composition, and when you do this composition here, that is when you do A, and then you do projection of A. What it means to be a split exact sequence, we'll talk about this later, is that both ends have the maximum white are called splittings that compose back these to the identity map. Turns out when you have a split exact sequence, the middle is always isomorphic to the direct sum of the ends. However, just because the middle is the direct sum of the ends doesn't mean that it's a split exact sequence. We'll look at an example of that later. That's a little bit harder to come up with. Okay, any questions on this? Okay, I'm going to write down a theorem that is basically from your homework, just kind of for your notes, if you will. So suppose I have this diagram. Actually, everything's been. Okay, so I have this big mess. All of these are R modules. This is a commutative diagram with exact points. So 644. Given this diagram, of our models with exact rows. So let me give you a quick kind of reminder. The commutative diagram, that doesn't mean anything about the ring. What that means is if I start and follow my nose anywhere I want, so if I start with A1 here, and then I take this map and this map, I get the same result if I had taken the different paths. So what it means to be a commutative diagram is if you start at the same place, you take two different paths to the same place, you get the same. And the rows are exact, right? So that means I don't know much about F1, but I do know that the image of F1 is the kernel of F2, the image of F2 is the kernel of F3, and so on. So we have this commutative diagram of R module homomorphisms with exact rows. Then if G2 and G4 are onto, let's get this one, G5 is 1 to 1, and G5 is 1 to 1. Then G3 is on. So in other words, just I think this is kind of amazing that only this information gives us away. But if G2 and G4 are onto, and you also have the G5 is 1 to 1, then it turns out that the one between G2 and G4 is also onto. And there's kind of a dual result. If G2 and G4 are 1 to 1, and G1 is onto. So now, if these two are injective, and this one on the left end is onto, then the one between the injectives is injective. This is called the phi lemma. Popularly called. And I'm not going to prove this because it's a homework problem, but I'm going to do you a big favor. I'm going to prove short phi lemma, which will kind of help you out, I think. Let me give you a corollary to this. Put over here, corollary to 645. Given the following commutative diagram of R module homomorphism, consider the commutative diagram of R module homomorphisms with exact rows. So here's my diagram. Zero, A1, A2, A3, 0. And then if G1 and G3 are onto, so if G2, if G1, G3 are 1 to 1, so is G2, and 3 if G1, G3 our isomorphisms. So is, by the way, I think the third statement follows easily from the first two, correct? This is pretty immediate from the 5 lemma, right? Because here, what we have is 0, 0, 0, 0 on the ends, right? And so the only G1 from 0 to 0 is the 0, it's just the 0 homomorphism from 0 to 0, which is both 1 to 1 and onto. So these like bonus conditions here that you need, you get automatically, right? And so this follows immediately from the 5 lemma. But since I didn't prove this, I'm going to prove this directly. And I think this will give you, this is one of the most fun things that you can have in any math class is to do a diagram, Jason. By the way, I hate to break it to you, but this is going to be a lot more fun for me than you because you have to write down the details and I'm going to kind of draw pictures here a little bit. But anyway, I'll give y'all some latitude on that. That's why I only wanted you to prove one of these things. Like I said, the proofs aren't hard. It's just you've got to go back and make the statements about who's where. Okay, this is, by the way, called the short file lemma. 5 lemma and short file lemma, exact sequences. So so I am going to do this mostly by just the diagram here. And I won't write a whole lot of detail. Try to do this one time. Okay, so let's go through our chase here. I am armed with some pretty colors here. Okay, let's prove this first statement here. So G1 and G3 are onto it. Right. Our goal is to show that G2 is onto it. How many of you have seen a diagram chase before? Okay, so our goal is let B2 be a B2. I've got to find something that goes to it, correct? So I have B2 right here. Now, I don't know that there's anything that goes to this. And if you think about it, there's only one way that there's only one thing I can do to B2, and that's push it down here by H2 to some B3. Correct? There is something that goes to. Now, what do I know? I know the G3 is onto, right? So don't know much, but I do know there's something up here that goes to B3. Okay. Well, I can actually pull this back, can I? Because what do I know about this top row? It's exact, right? So that means that there is something that goes here, right? A2 goes to A3. Right? So what my diagram means, of course, is H2 of B2 is this, G3 of A3 is this, and F2 of A2 is this. Everybody okay so far? Now I'm just dying to be able to go down here, right? But I don't really know that, right? What I do know is A2 goes to B3. I don't know that it goes to B2. All I do know is it goes to some X here, right? So I haven't really discovered that this is onto, because all I know is that A2 that goes to the same place as B2 does, but go all the way around, goes to some other X, right? Any idea how we might be able to move forward? from this because it looks like I'm out of aces.
It needs to be mapped to be figured out because we didn't map it.
Correct. The diagram commutes, right? So if I start here, when A2 walks this way, it goes to B3. When A2 walks this way, it has to go to B3, which means whatever this X is, it's got to also go to B3. Right? X and B2 may be different, but they go to the same place. Right? How does that help?
In the kernel.
Aha. So let's say B2 minus X is in the kernel of H2. Agreed? Okay. And lo and behold, this bottom row is exact, so that's in the image of H1. So what can I do with that? Well, what I could do with this is there exists some B1 that goes to, how did I do it? B2 minus X. Agree? Because the fact that B2 minus X goes to 0 over here means there's something that goes to it here because it's an exact sequence, right? And lucky me, I can pull this B1 back here. Everybody agree? So let's use the commutativity of the diagram again. A1, when I start A1, it goes down here. Here goes to B2 minus X. So this goes to some, let's call it Y. And Y goes to B2 minus X. And can anybody tell me how this helps? So that is to say, what we've got now, G2 of Y is B2 X. Let's not lose sight of our goal. What we're trying to do is find something in A2 that goes to our initial B2, right? I know that this thing goes to B2 minus X, almost. And A2 goes to X. So if you look at G2 of Y plus A2, this is G2 of Y plus G2 of A2. And G2 of Y is B2 minus X. And G2 of A2 is X. How about that? So G2 is on tag. Everybody follow that? Yes. Okay. Everybody okay with that? Let's try another one. Let's do the one-to-one statement. And of course, I'll skip statement 3 because if it's one-to-one and off and onto it, it's nice and nice. Okay, let's try this again. The second thing we want to show is, let's suppose for our second statement that both G1 and G3 our burden is we want to show, so these are both 1 to 1 here. We want to show that this is also 1 to 1. Okay, so let A2 be in the kernel of G2. And when I apply G2 to this, I get 0. And somehow I need to conclude that A2 is 0, right? And then I'll be happy because it'll be 1 to 1. Everybody okay with that? Now, of course, 0, I can push it on or pull it back, but 0 just, it's not really very helpful, is it? Right? So let's play off this. Again, I've only got one thing that I can do, and that is go forward, right? I can push this forward to A3. And then I guess I've only got one direction to go here. Let's go down here to B3. But can anybody tell me what A3 has to go to here? It has to go to 0. Somebody tell me what? That's right. This goes to the same place. A2 goes to 0, so it goes to 0 here. So that means that A3 has to go to 0. Everybody agree with it? So G3, what conclusion can I draw from that? A3 must be 0 as well. G3 was 1 and 1. Right, we assume that. So this is actually 0. And that gives me more information, right? Because that means that A2 goes to 0, right? So F2 of A2 is 0. So A2 is in the image, or I'm sorry, in the kernel of F2, which is the image of F1. Right? So what does that mean? That means there's an A1 that goes here. All right. So that's kind of cool. At this point, what I've learned is anything in the kernel here, there's something that goes to it here. Now, goodness, I'm almost out of real estate, so let's just follow this again. A1 goes down here to B1. And when B1 goes over here, where does B1 have to go to? It has to go to 0. Again, this is that diagram commuting thing. Going this way is the same as going this way. That forces B1 to go to 0. So H1 of B1 is 0. But H1 is 1 to 1. So B1 is 0, right? So B1 is 0. So what do we conclude about? So A 0 is B1, which is G1 of A1. Then A1 is 0, and G1 is 1 to 1. So this is 0. Therefore, A2, which is F1 of A1, which is F1 of 0, is 0. So G2 is 1 to 1. And that establishes the short pipeline. Any questions on that? The 5 one is very similar. It's just a little bit more complicated because we're not assuming that these are 0 here, so this is not necessarily on to, but the same ideas will carry the day on this. Okay. Any questions? Questions on that? Everybody follow that? Okay, so now it's time for Hollywood squares. So So we're going to consider following diagram of R module homomorphism, commutative diagram. Let's say yes. 6. Consider the following diagram of R module homomorphism. Has anybody got a computer or phone that they can look at homework 2 for me? I'll ask you questions in a minute. Let me break the diagram out. I'm not going to put the maps in this one. Okay. This is by the way, this is called 3x3 lemma. Okay, so what is the content of 3x3 going to say? It says if the columns in the bottom 2 rows are exact, then the top rows. Bottom 2 rows. Exact. Then top rows. If you're looking at the homework, is this the one that I claim that I approved in class?
Yes.
Yeah.
Okay. Well, this is a whole program. The one that you're supposed to do on your homework is the dual one. That is the columns in the top 2 rows are exact. Then bottom rows exact. So let's see if we can fight our way through this. So we will endeavor to show A, B is a homework exercise. Okay, so let me write kind of a more dramatic version here. Race and fair, I think. I will only write maps, names of maps on a need to do basis. Although, here's the hypocrisy of lecturing about this. You should be a little bit more explicit to me when you write it down and try to tell me in your homework. Okay, so when I have to show, so what we're trying to do here is we're trying to show the exactness of top row, right? Given that the columns are all exact and the bottom two rows are exact, right? So what do I have to do? I will write this. Let's see, one just in case. So I've basically got four things to do. I have to show that F1 is 1 to 1. I have to show that G1 is onto. I have to show that the image of F1 is contained in the kernel of G1, and that the kernel of G1 is contained in the image of F1. So there's four things that I got to get taken care of, right? And I never remember how this works until I do the proof. But either 1 to 1 here is easy or onto is easy. And whichever one is easy for me will be hard for you. And whichever one is hard for me will be easy. It's funny how it duels out like this. The containment, the image is contained in the kernel will almost always be easier. The kernel contains the image will be a little tougher. So, all right. I don't know which one's the hard one, but we'll see. Right? Let's experiment. Okay, so first, let's try F1 is 1 to 1. All right, so let's let A1 be in the kernel of F1. So we've got an A1 here, and all I know is it goes to 0 here. Right. Now I want to show that this is 0. Agree? So let's chase this, and the only way I can see to chase it is this way. This goes to B1 here. Now, of course, everybody agreed that 0 goes to 0 here. If I chase it down here, right? Because 0 always goes to 0. Agree? So that B1 goes to 0 here. What does that mean about B1? Because it's 0 because I know that this row here is exact, so this is 1 to 1. So B1 is 0. And the columns are exact. So this is 1 to 1. So A1 is 0. So check. F1 is 1 to 1. Everybody agree with that? I think that's going to be your hard one on the homework. I think my 1 to 1 was easy. My onto is going to be hard. Let's check, shall we? Is everybody okay with this so far? Let's do the onto business. Let's see if that's a little bit more work. I bet it will be. Let's do G1 is onto. Okay, so here we'll let A3 be in A3. And we need something here that goes to A3, right? Well, I mean, geez, if I could pull it back here, I'd be done, wouldn't I? Right? So there's really, I like this in the sense that I only got one choice, and that is just push that down here. B3. Let me also point out that the columns are exact, so I can push this down to 0. Everybody agree with that? So when I go from A3 to B3, the image of this is in the kernel of this, so B3 has to go to 0 down here, right? Now, I think probably the important thing is now that I'm down in this row, I know this is exact. So this map right here is on to. Agree? So there's a B2 that goes to B3. Right? Agree? Well, I guess what I'm gonna have to do is go down here. Let's go to C2. And now I see a little light of day here, because where does C2 have to go? Because of the commutativity of the diagram, C2 has to go to 0. Agree? So now there's a C1 that goes to C2. I am getting way far away from this, right? I'm gonna start to lose a little confidence. I'm getting a little shaky here, right? But there is a C1 that goes to C2 because of the fact that this is exact. Everybody okay with it? Now, lucky me, I can keep the spike going because this column is also exact. So there's a B1 that goes here. Right? Now, when I do this dance here, B1 goes to C2. B1 has to get to C2 this way as well. Agree? It's just, there's no reason for me to suspect that it goes to B2. So maybe it goes somewhere else. Let's call it to X, which is also in here. Notice X and B2 both go to C2, right? This goes to some A. So B2 goes to C2 and X goes to C2, right? Everybody agree with that? How does that help? Anybody remember kind of the trick? How that help? Their difference, right? B2 minus X is an element of B2. And that's in the kernel of this map. So there's an A2 that goes here. Agreed? Now, my question here is, where does B2 minus X go over here? So let me call this map G2. What happens to G2 of B2 minus X? Well, this is G2 of B2 minus G2 of X. G2 of B2, I know, that's B3, right? I agree. Can somebody tell me what G2 of X is? G2 of X is C. Look up the line. Right, because X is in the image of this middle map, right? So I go B1 to X, and then when I push X on, it has to go to 0 because that row is exact. Right? Everybody okay with that? So B1 to X, X to 0. So if I look at B2 minus X, it goes to B3. Everybody agree with me? So let's look at where A2 goes over here. A2 goes to Y. And this goes to B3. So A2 goes to B2 minus X, which goes to B3. Agree? A2 goes to Y, and Y goes to B3. So let's see what I've got here. G1 of A2, I'm sorry, yeah, G1 of A2 is equal to Y. And where does Y go? Y has to also go to B3, doesn't it? Because the diagram commutes. This goes to B3, so Y goes to B3. So we'll call this something. We'll call this a oh, right. I kind of lost sort of what I'm doing here, but so notice that I'd like A2 to go to A3 because that's the whole point, right? I want this to be onto, well, it goes to Y, but let me call this map something H. H of Y is equal to B3. And that's also H of A3. Right? What can we conclude? Y equals A3 as H is 1 to 1, right? Because it's the first map in that exact column. Therefore, G1 of A2 equals Y, which is A3. So G1 is on 2. Okay, that was a hard one. Would everybody agree that the 1-to-1 was significantly easier? I mean, look at that. I went everywhere except the upper left corner in this one. All right. Crazy. Okay, any questions on that? Okay, so I think I'll probably just put the diagram here. This is quite a mess. Okay, so now we need exactness in the middle. One of these will be easy, and one of them will be more difficult. I'll see if I can pull this off. Well, then what it means. Okay. Now what we need is, let's go for actually, I'm going to go back to the let's do the image of F1 contained in the kernel of G1. That's half of what I need for exactness in the middle, right? So let's go for it here. So basically what we have to do is show, so let me give you kind of an alternative characterization of this. That's really what you have to show, that when you compose F1 and then G1, you get 0. That's it, right? So let's start with an A1. And basically what we have to do is show that if I bounce it twice, it's 0. So this goes to A2, right? And this goes to A3. And we, of course, we need to show that A3 is in fact 0, right? Well, let's bounce this down to B1. And that goes over to B2, right? And notice, I'll just make the observation as I go along that A2 goes to B2, right? Now, where does B2 go? B2 has to go to 0 because that second row is exact, right? And again, the diagram commutes here. So A3 has to go to 0. Agree? And that's really all I need, because what do I know about this function right here? It's 1 to 1. So A3 is 0. And there we go. Fine. That one wasn't too painful. Let me now add some pain. Central. Oh, this is okay, so the final bit is to show that the kernel of G1 and the image of everything. Okay, so let's try to get through this, see if we can do this. So let's suppose that A2 is in the kernel of A3. All that means is that goes to 0. Right. We have to find something in A1 that goes to it. Right, that's our burden is to find something in A1 that goes to statement of purpose here. Find A1 and A1 such that F1, A1 is equal to. Okay, so let's chase. This goes to B2. And of course, that 0 goes down to 0, which means that B2 goes to 0. Agree? Now, this means that B2 is in the kernel of this map, which is the image for this map. So there's B1 that goes here. Now, unfortunately, I can't really pull this back, at least at this point. So all I can really do, I guess, is go down here to C1. And let me also note that B2 must go to 0 here, because again, the columns are exact. So when I push it twice, it's 0. Agree? So C1 goes to 0 here. Agree? So that means that C1 is equal to 0, because this is 1 to 1. That means that B1 goes to 0, because C1 is 0. So that means that B1 is in a kernel of H2, if I call this H2. So that means that there's something that goes to B1 up here. Call it A1, or well, let's call it. Yeah, I'll call it A1. I may have to change my notation here. So A1 goes to B1. Now, I guess the only thing I can really do is chase A1 over here, and I will. So A1 goes over here to X. Right. And where does X go? Oh, well, that was an undefined question, wasn't it? A1 goes to some X over here, and where does X go if I push it down here? It must also go to B2. So X goes to B2, and A2 goes to B2. So what can you say about X and A2? Right. Well, so X goes to B2 and A2 goes to B2. So X minus A2 is in the kernel of whatever I call this map, K1. Well, what can you say about that map? It's 1 to 1. Therefore, X equals A2. Right? So in other words, F1 of A1, which is equal to X, is equal to A2. And so A2 is in the image of something over there. Any questions on that? That is a diagram chase, right? So hopefully that'll give you the idea of how to kind of approach this sort of stuff on the homework. Try to digest this and, let me know if you got any problem. I'll try to help you sort through it. Any questions? All right, I will see you all on Wednesday.